Okay, so this is we're going to continue our, I guess, skipping of the stone across the pond that is machine learning. So by this point, I would hope that you at least have some idea that you have a model that solves problem one. Notice I didn't say a good model, a perfect answer. But hopefully yesterday you were able to get something and you saved it. If you're sitting there going, it didn't work ever, please talk to me. Before you leave, I want you to have the experience of actually taking in your own data and training an algorithm. There will be a solution, a really nicely written solution from a data scientist to this hackathon problem in the notebook we'll be using today. So don't panic, it'll be okay. You should understand how to construct a model. That model equals, you should understand that you need to compile it, and then you need to know how to call a model.fit. And then you should also have some idea of these basic parameters for your model. And by that I mean, like, how many nodes in each layer? How many layers do I have? What activation functions am I using? Those things that have been fairly arbitrary because we haven't taken a deep dive, but they exist in that model equal call. So I have that model. I'm done. It's got 2 days left. I solved the problem. Rarely ever works this way. So in an analysis, in a physics analysis, right? I remember back in grad school, I did my analysis, my thesis analysis. I had top line results. Everything was great. And then I had to spend the next few months doing systematic studies, right, to get my systematic errors. And you have to do this for models as well. You kind of. The analogy kind of breaks down a little bit, but the systematic errors on your analysis is kind of like, what if I would have done things differently? And you need to answer that question for your model. So one of the methods, or I guess one collection of methods, if you will, for doing this refining and training of model development training is called hyperparameter optimization, or HPO. And so it's essentially trying to answer this question of what if I did things differently. If we had a lot more time, what I would have done is said everybody used MSE as their loss, which means you can compare apples to apples, turn to your neighbor and say my overall loss was 94.8. And then your neighbor will go, mine is 87.6. They got a better model than you did. And so you would compare your results and see that not all models were created equal, even if they had the same topology. That's interesting. Okay, so we want to basically go through the process, if we were really solving this, of saying, you got a better model than I did. Is there a better model than that? What if I would have not used 2 layers, but 3, or 1, or 28 nodes instead of 16, or whatever that happens to be? But then you also have these other things like maybe somebody used stochastic gradient descent. That's not Adam. That can affect how you're traversing that error surface. So maybe the method you traverse that surface is different. Maybe you could have gotten a better model using a different method of traversal. The learning rate is bundled in the optimizer. I can go on and on and on and on. Basically, every choice that you made, every little variable in the lines of code that led to your training is essentially the hyperparameter space. There are a bunch of packages, and I thought I would go to Google and start pulling out them. And then I was overwhelmed, and I thought I didn't want to advertise any specific ones as if there was just one or these are the best. It would have been arbitrary. But you can literally go machine learning HPO package, and you'll get a whole bunch of them. And they all rely on various methods. There's grid search, which is the easiest. So let's just take, for example, we have 2 hyperparameters. We have number of layers and number of nodes in each layer, right? So I could set up a grid that says 2 or 3 layers of 10 or 20 nodes. A grid search would be try all combinations of those values choose the best one because I gave you the best model. There are other Bayesian and probabilistic methods, which are really interesting. And I left, I kind of stole the hyperparameter optimization from a colleague who is actually setting up ML flow at Jefferson Lab to be used site-wide, some extra handy tools. And she put in the bottom half of this, the hyperopt method, which is to me beyond the scope of this, but hey, you like the idea, you want to explore it, it's there for you. You can take it back to your home institution, play around with it, please. We'll be sticking to grid search, something rudimentary, brute force, and easy to understand. I could definitely spend a week just on hyperparameter optimization, how to do it efficiently, what packages there are, what methods there are. But that's not what we're doing. We're not doing theory. We're doing experimental stuff. So we're gonna get our hands dirty. We're gonna be using ML flow, which is this package which is not specifically a hyperparameter optimization package. It's more of a method of keeping track of your models, what the models are for, the code that goes in, the data that goes in, the configuration. But if you start doing this by hand, right, you start noting in your notebook, I use this configuration, this was my loss. I use this configuration, this was my loss. And when you have that information saved, you can then query that database, if you will, and say, give me the one with the lowest loss. What model did it look like? So one thing that we will have to do in order to get this to work, and I would encourage you highly to take the model you developed yesterday and drop it in the code in place of this model. Now, this doesn't look like model equals. Sorry. There are 100 ways to skin this cat. Oh, wait, no, there, model equals sequential. So you can either establish a model by saying it's a sequential with these layers, all in parentheses, or you can say my model is sequential. My model should add this layer. My model should add this layer. My model should add this layer. And you can pick whatever layers you want and whatever you want. So this is instrumented. And what I mean by instrumented is instead of manually writing a model equals and then going back and manually writing, she made this function, says create sequential deep neural net. And there are parameters. The width, this is 900. This is the width of the input. And why do you need to know that? Because the first layer needs to be your input layer, right? And the last layer always needs to be the number of outputs you need, which is 3. So she made this function. You could put 4 in if you wanted, and you could use this to harness whatever model you're working on. You don't have to make it as fancy and complete, but you need some way of saying, hey, I need to try out different sets of node numbers. And you could use this as a guide to try to instrument your model in this method. And then once you do that, this long thing, which is actually cut off, right? You go a little cross-eyed, don't worry about it. What this is doing is saying for every possible hyperparameter, we're going to do a grid search. So just like if I have 6 for loops, I get every combination across all those hyperparameters, and that's what this says. So you can pretty much steal this. It's in there, and your function will be, you modify create sequential DNN to be your style of model. And you'll see in the Python notebook, there will be a place at which in this loop, it's creating a model, it's setting an optimizer, it's compiling the model, and what's cut off is you fit the model in a loop. So it comes back through, it gets a new set of hyperparameters, it builds a new model for us, it sets the same optimizer. Excuse me. This learning rate is a variable that she used as a hyperparameter. It's fine. So you make a new optimizer, you compile it again, you fit it again, you go to the next grid space, you do it. And instead of having to manage it, we're going to end up having ML Flow manage it. So I did update these slides. You can download them from the Indico link if you want to, an up-to-date version. Otherwise, there is one Python notebook. Upload it and start working through it. It's based a special attention, to where you are setting up your grid search. And if you are failing to see it in the code, raise your hand. I'll come point it out. It should be pretty apparent. My one word of caution: if you're doing a grid search, right, and I have the combinatorics can grow quite quickly. So don't do too many tests. Don't set up 8 possible sets of activation functions, 10 possible batch sizes, 20 possible number of layers. No, it'll take a long time. If you want to go back to your dorm and then do that overnight, go for it. Go for it. It's interesting. It's fun. And then hopefully what you'll come away with at the end of the first half of that is you'll ask ML Flow, what was my best model? And I hope it's not the model that you started with. It'll be a better model. All right? Yeah, question?
ML Flow like a topper for TensorFlow, or it's a swap?
It's a topper. ML Flow isn't specifically tied to TensorFlow, but they're borrowing the branding. So yeah, it's just a database, the way to record your models, and it'll all be in there. Yeah, keep going. Raise your hand if you have questions. I'll be around. Let's make some more optimal models.
Okay, so yeah.